Hi, everyone. Thank you for this opportunity to have this talk. And yesterday we have a lot of discussion about getting AI ready. I guess I can share a bit about what I think about getting AI ready as well. And so I'm Chung-Han. I'm from Center for Advanced Microscopy at the Australian National University. We are a node of Microscopy Australia that has a supercomputer on campus across the street from our center. We have a full suite of cryo instrumentation co-founded by Microscopy Australia and the ANU. That includes gel cryo-TM instruments, cryo-arm 200 and F200 and a focused ion beam SEM Zeiss Crossbeam 550. The whole cryo suite can generate data close to 1 petabyte a year. So to accommodate that kind of big data throughput, we mainly collaborate with the national computational infrastructure. However, turning computing resources into microscopy services isn't always straightforward. We found that it is also very important to make sure that our current research data infrastructure can be as scalable as possible, while making it suitable for AI-centric and also be able to underpin microscopy research applications. So today I would like to give a bit of picture how we approach this at the ANU camp to further build a scalable research data infrastructure for microscopy and getting AI ready. These are the main instruments at ANU camp that I just mentioned, and then they generate research big data. I will go through what our research infrastructure looks like and how I blend camp's digital infrastructure with NCI's supercomputer environment. I will also briefly talk about what has been updated with our new cloud deployment and how that can contribute to the scalability and help with getting AI ready. As you can see here, on the left-hand side, that's CAM, and then on the right-hand side, that's NCI. We are co-located just across the street from each other. In terms of computer networking, geographical location sometimes does matter a lot. And NCI's internal switch is directly placed at our location, our area. So in 2022, we established CAM NCI data infrastructure with the cryo workflows to provision digital services for meeting our needs in compute, storage, and network for our advanced microscopy imaging techniques, including single particle analysis, cryotomography, and microelectron diffraction. The established data infrastructure enables real-time processing and minimizes pre-processing turnaround time. Last year, we completed the deployment of self-hosted global server endpoint and integrated between institutional accounts and NCI user accounts. This makes the global data transfer services more seamless and reliable to users. So whenever we would like to deliver large data set to users back to their home institution, we simply let the users to use Globus to do it. That has been very helpful for collaborating with, for example, CSIRO and other international academic institutions. So NCI houses the GIDE supercomputer, the biggest supercomputer in the Southern Hemisphere, with more than 4,900 servers. ANU and NCI are currently doing the upgrades to align with next generation AI-centric supercomputing. NCI also has Nearing Cloud that provides a self-service cloud platform through OpenStack technology, where I can easily launch a new virtual machine and have a fast deployment for new applications. They also have an open on-demand platform called AIE, Australian Research Environment, that allows us to launch a GPU-enabled virtual desktop anytime from a web browser. And Nearing Cloud was repurposed from NCI's previous generation supercomputer called RIKEN. Nearing Cloud mainly serves CPU-based cloud instances only. So deploying the very first global server endpoint on Nearing Cloud in 2024 allowed us to easily deliver research data to external users. However, the global collection that we established is based on GIDE's raster power file system called GData, which is relatively expensive, and GData is meant for being used with the GIDE supercomputer for high-performance computing. To use our storage space more efficiently, I decided to deploy a cloud-based object storage cluster on Nearing Cloud and connect the cluster with our existing global server endpoint that is already on our Nearing Cloud deployment. This way, we have the flexibility to use the cloud object storage system as the data lake to let users and staff put away raw image data, whereas the GData global collection is the storage space also used with our processing software with GIDE for parallel computing directly. This is the Global's web-based platform where our users can easily find both Global's collections to access their research data sets. We are the very first at ANU who integrates NCI accounts with ANU's email accounts. So our users and staff can simply log in with ANU account, no longer need to use two accounts back and forth. This infrastructure is also with the great help with RNet. For example, when doing single particle analysis, if we want to deposit or retrieve data sets from Empire data repository in Europe, we can simply do that within a few clicks through RNet and Globus. To implement cloud-native object storage system and connect with our global server endpoint, I choose MinIO for the system core and Nginx as the load balancer. And I wrote Ansible script to deploy them in multiple nodes in multiple drive fashion. Because our systems are based on Nearing Cloud, which is an OpenStack system, it also allows us to access the cloud infrastructure through OpenStack's APIs. It means that we do the deployment in an infrastructure as code practice to automatically launch multiple virtual machines, create storage volume, configure the virtual machine, etc. So far, after the whole deployment, we also have achieved 1 gigabytes per second effective transfer speed with QuizCloud RDM through RNet this year. If we would aim to scale the system for more storage space, our research data infrastructure can be scaled out and expanded with more nodes. The same thing could be implemented for our global data transfer nodes for more bandwidth. We have 8 data transfer nodes in place for our global server endpoint and another 8 nodes in place for our MinIO cloud object storage. This cloud-native object storage ensures us the scalability of our current research data infrastructure. There are ways to actually virtualize both of the HPC storage and cloud storage in a single namespace, but today I won't be able to go into it, but I would love to share if you come to me, ask questions afterwards. And another reason why we choose implementing MinIO is not just to have high flexibility in managing the data infrastructure by ourselves, but also to get ready for AI as a microscopy facility. What exactly do we mean by getting AI ready? The research data that we generate from our scientific instruments can easily be accessed and used for AI training and inferencing. The AI that we are after are mainly for many AI-based computer vision and natural language processing, as well as microscopic control code generation. And because the research data generated from our microscopy facility also has the nature of write once, read many, this is exactly that a cloud-native object storage like MinIO can offer for AI training and inferencing for research activities. Most of the major large language models were trained through object storage, like, for example, from Anthropic to OpenAI, they all use object storage. Another example is that POSI Supercomputing Center also implement MinIO for their research data infrastructure in Bankshot system. So when we are talking about easy access, it means that MinIO has the full compatibility in supporting AWS S3 APIs. This allows many customized software applications or programs to access data directly. For example, if we would like to let AI training PyTorch script to run data loader, to map, to iterate through data files, we can easily do that through MinIO's S3 APIs. And because we are hosting it by ourselves, we ensure that it is private and it is local to us and users. More importantly, the object storage can be evolved into new cloud-based emerging data lakehouse for AI. Recently, just in July this year, AWS released AWS S3 Vectors Preview, which is the first cloud object storage with native support to store large vector data sets. Vector search is a new emerging technique to also let generative AI or large language model to search into a connected vector database for local knowledge in numerical representation, and being able to provide combined generative responses to users. So this is called Retrieval Augmented Generation Large Language Model technique. In the conventional research data management, we have to do data modeling and shape what kind of metadata we would like, ingest into relational database, develop programs to create, re-update, or delete, and do analytics for data sets. But now with generative AI, RAG-based LM techniques can also complement our research data infrastructure and speed up the development. And one of the essential part of the infrastructure is cloud object storage, and vector database can be built upon object storage. We also see that in the very near future that the model context protocol will be available on many microscopy instruments for letting AI and large language models to be able to control microscope with their generated control code, same as the vector database. So AI can access the database directly. But come back to generated control code, I will see the code and also the metadata responses will largely depend on the local knowledge that we put into vector database. That way, as end user, we can use microscopes more easily and access research data with human natural languages in just few sentences. And just a remark, right now we are testing our large-scale large language model with 120 billion parameters within our facility, and it has been very, very promising as well. Thank you.